Hello again. Thank you, Chabi, for the introduction. I will continue today in my talk about multi-microphone speech enhancement, specifically about source counting, diarisation, and speaker separation. Since this is the second part, I will have a brief slide, one slider that will explain what are the intermediate summary of what we had before. So I'll go immediately to this slide. And I want to actually more or less to remind you what we have established in the first part of the talk. So first of all, we are talking about beamforming algorithms. There were multiple criteria: LCMV, MVDR, multi-channel Wiener filter, and so on. The LCMV will be the major algorithm that we will use, since it is capable of dealing with specific sources. Since usually in our environment, in our scenarios, there will be several speakers in the environment. Some of them are desired, some of them are interference. We will have to deal with each one of them separately, and the LCMV gives this to us quite easily. So this is why we are using the LCMV criterion. All the other criteria are related to the LCV. We showed this last time. Another important topic that we spent some time on it in the last meeting is the fact that we like to have beamformers that are acoustic aware beamformers. So they take into account the acoustic propagation rather than just the delay only as in classical beamforming. So they take into account the fact that when sound propagates in regular room environment or regular acoustic environment, it reflects on all the object, the room facets, and so on. And this is why there is a very large multipass relating them, and we should take it into account. We show that taking it into account can allow us to perform much better beamforming, with much better resolution, even with a few microphones, which is very important for our application, in which we have for now 4 microphones, or maybe later we'll have 8, but this will be the maximum. We also established the relative transfer function, which is nothing but the ratio between the transfer function of 2 microphones, or 1 microphone towards one of the reference microphone. And we already mentioned that we can blindly estimate it from the data, and that we have a plethora of algorithms that can do it. We will specifically discuss one of the algorithms later today. So maybe the main idea is that we want to have acoustic aware spatial filtering and not only delay only and so on. What is missing, of course, when we are constructing our beamformers is to know what are these RTFs, which constitute steering vectors of the beamformer. So this is one thing which will be very important. On top of it, we would like to associate the RTFs, which is a bit abstract vectors, to a specific location that will allow us to analyze to spatially analyze the environment. And we also we saw that in all algorithms, we need a noise spatial correlation. So we will have to discuss how we do this, and how, as Radu asked last time, how do we control the beamformer? How do we construct all its building blocks? So this will be the first topic now. So we need to know the RTFs, and we need to know the noise correlation matrix. The RTFs, as we mentioned, we have a lot of algorithms. However, most algorithms require some type of knowledge about the activity patterns of the speakers. So if the speakers are polite and introduce themselves, then we can estimate their respective acoustics while they are speaking alone. However, we cannot guarantee such a behavior in most real-life environments, and this is why we will need something which is more flexible than a predefined activity pattern of the sources. We had some other ideas, but I will concentrate here on one of the ideas. Another thing that we can apply here, which we still should do during the project, is to add other sources of information. I would call it external sources of information or side information. And video is, of course, a very good candidate. Also, speaker identification, language, and so on can be used, but video looks like a very very specific candidate that is already used in many algorithms, and we would like to incorporate it into the activity pattern identification that we apply here. In general, we looked in my group. We looked at several algorithms to control the beamformer. One of them is based on DNN, another one based on variational base. Also, one worked together with the INRIA group using the variational base or variational EM algorithm. But here in this talk, I will concentrate or focus on the third family of algorithm, which is based on simplex analysis. But all the others are still valid algorithm, and I think that they deserve more research, and probably we will do this during the project. Another issue that we have to take into account is the fact that the number of microphones is limited, and whenever we design a beamformer, one of the requirements that we had was that we'll have more microphones than sources of interest. But what is happening if there are more, if there's just larger group than these 4 microphones? So for this, we are in the regime of underdetermined problems, and we had to take care of this as well. This will be related to the activity pattern that we will estimate. I will talk about it in the next slides. So we here focus on the simplex-based analysis that we are using. We use it both for diarization and separation. Sometimes if one speaker is speaking alone, we do not need to separate, but just to extract the specific speaker from the audio stream. And on top of it, we will use time frequency masking. The fact that in each time frequency bin there is only one dominant source, we will utilize this in order to have even better beamformers, and also to apply some type of post-filtering, which I mentioned briefly also last time. But this post-filter that I will discuss today is inherent part of the algorithm. So these will be the topics of what I talk today: how to estimate the activity pattern of the sources, and then to utilize it in order to construct all components of the beamformer. So let's start with the specific environment. So as I said before, like you can see depicted here in this figure, we have 6 speakers, but only 4 microphones. So the problem is globally underdetermined, so more sources than microphones. However, we can assume that people would not speak all the time concurrently. So the number of locally speaking speakers, or the instantaneous number of the speakers, is usually smaller. What we see here, for instance, is that only 2 speakers are speaking, and then 4 microphones are enough, although there are 6 people in the scene. Of course, we do not know the activity pattern, and we do not know when each speaker is speaking. So we need to extract the sources. For instance, here we have 2 sources, so separation is mandatory, but also this diarization, which is actually an answer to the question, who speaks when? So let's go to a mathematical model. I start with a noiseless case. Of course, there will be noise in our environment, and I will discuss it a bit later. But most of the concept can be explained easier in more easy way while talking about the noiseless case. Afterwards, we'll add the noise, and we'll see what are the consequences of adding the noise. So the model is a bit different from the regular model, in a sense that we have included here an activity indicator, this I. This ij of L can take values 1 or 0, and ijl becomes 1 if the j speaker is active during the Lth frame. So this is frame-based indicator, and each frame is indicated by the number of speakers in the scene. H is the transfer function, S is the source. We have J sources. And we already saw that we can recast this problem into the problem of using the relative transfer function, where the reference microphone serves as the input. We talked about the relative transfer function before, and I will mention it later again, but the main issue here is the fact that the relative transfer function is relating to measured signal. And since there are two measured signals, the estimation of the RTF becomes a non-blind problem. This is much better than the estimation of H, which is relating the source, which is unknown, to the microphone signals which are known. So the ATFs are, the estimation of ATF is a blind problem, while the estimation of the RTF is non-blind. Okay, so when we look at this formulation, we are saying that in general, the number of speaker J is larger than the number of microphone M. However, JL, which is the number of concurrently speaking speakers in each frame, this JL is smaller than M, meaning that the problem is locally overdetermined, and I can apply any beamformer that I like, and specifically we'll apply the LCV beamformer or its variants. So what do we do if we have this type of activity? So we have to decide what is the activity pattern. Of course, we will discuss soon how do we do this. But if we decide that there is no active speaker, then the output can be 0. So we don't need to do anything. If we decide that only one speaker is active out of the scene, so then we can just take the reference microphone as the signal, and this will include in these frames only one speaker, and it can be used for further processing in the ASR system and the language model and so on. If there are more than one speakers, but still recall that it's smaller than M, the number of microphones, then I have to apply some type of separation. And for the separation, I actually applied the LCV beamformer, which becomes, in the noiseless case, it becomes just a matrix pseudo-inverse. So the pseudo-inverse of this constraint matrix. The constraint matrix is related to the estimated RTF, which we still need to estimate. So we have several options, and all of them are controlled by the activity pattern which we need to extract from the data, blindly extract from the data. And I also denote S of L, this calligraphic S, as the set of all active speakers per frame L. So all speakers for which the indicator is 1.
Sharon?
Yes.
Did you define C already?
Yeah, I did it in the first part, but C is the easiest way to do is to have all RTF as vectors of this matrix C. So if you have JL vectors of active speakers or active RTFs, so it will be M times M due to the fact that we have M microphones, times JL, the number of concurrent speakers in this frame. Mm-hmm. So this is usually the matrix of, this is what we do here, is the matrix of RTFs. We showed in one of the slides in the first part that we can, if we have several speakers which are all active, probably simultaneously active, but are all of interest, we can actually extract several of them together without separating them within the group. This is very important while analyzing a conversation, but for the ASR it's less relevant, I think, since ASR will need each speaker separately. So for this I need to know each RTF separately. In the other application I can have a basis that spans these RTFs. this can go to C. This is why I called it C and not H, in order to distinguish between H, which is the exact RTFs, and C, which is a basis that can span them.
Okay. Thanks.
So all is left, which is quite a lot, but still all is left for us is now to identify S of L for each of the frames. So which are the active speakers in each frame and the associated RTFs. Okay, so this is the activity that activity set that we want to extract. We need the RTFs, as I said. This is mentioned here in the red block. So in order to do this, this becomes simple in the noiseless case, since I collect all frames in which speaker number J is speaks alone, solely speaking, and then I do simple system identification, which is depicted here. This is nothing but some type of Wiener inspired system identification, which is the cross spectra divided by the auto spectra of the specific speaker, and I do it while collecting all frames in which this specific speaker is speaking alone. And then you can also see that it's only using Z, which are the received microphone signal. So certainly this is a non-blind problem, which is very good. One thing which is less good is the fact that I have to collect several frames. So now it depends on the application. If the application is very dynamic, I have to take this set and split it into pieces in which I can assume quasi-stationarity. And this, I can already say that it's a drawback of the current solution, which we want to improve here, is the fact that how long or how many frames are we using, and are we using also frames from the future, which we don't want to use, of course. Probably we can allow some type of latency, since we already have a latency by the ASR system and communication with the cloud. So this we can allow, but not much more than this. So we have to be careful a bit with the selection of this L of J, this calligraphic L, but for now I assume that any frame that is available to me I can use. Then we can decide how many do we need to use in order to have a stable solution on the one hand, and on the other hand, not to introduce too much latency, and also to allow for dynamic scenarios.
Sharon?
Yes?
Could the video help you choose which frames do you sum over?
I think so.
Okay.
Yeah.
Then maybe we have
I can see, like from the lip reading, that which source is active. I think it can help. Okay. For instance, this is something from the back of my mind that I can immediately say, but I guess that we can do even better.
Okay, so we have to at least give it a thought to this.
Yeah. There were some papers that I saw recently using DNN, in which you have a video and you try to analyze which one is speaking out of which pixel is active, actually.
Yes, I know it.
I think from Facebook. So we can discuss these issues. I think it's very important. So now I estimated RTF. I don't want to get too deep into it, but just to be for the sake of preciseness, I would say that I concatenate several frames. I concatenate all the RTFs of all microphones. I take the real and imaginary part, and then I construct a feature vector, which will be helpful later. And so I have a feature vector for each. Actually, I can construct a feature vector for each frame, which I will explain soon how I work with them. There is some mathematical assumption which I explained, but I would like here to be more concise. These are assuming that the RTFs have zero mean and that they are uncorrelated. It's related a bit to the acoustics and to Schroeder equation, Schroeder work on acoustics in the frequency domain, but I think it will be too elaborated to discuss it here, and let's take for granted these assumptions. They are approximate. I cannot claim that they can be satisfied accurately, but still this assumption is good enough for us to continue. Now, we start with a very important concept which we use a lot, also in this work, but also in other works, which is called the WDisjoint Autoconnect assumption by Yilmaz and Reichardt already 15 years ago, even more than 15 years ago. And what they claimed is that if we look at the spectrogram that you can see here, then this is a spectrogram of several sources together. Then each time frequency beam, according to this assumption, is dominated by a single speaker. I'm not saying that the other speakers are inactive, they are active, however, there is only one dominant speaker. Indeed, and this is something that I verified experimentally, if you apply the STFT, by the way, they didn't use the STFT, they used other transform, I think Gabor transform, but it's not really important. But if you apply the STFT and you know somehow which source is dominant, which source is active in each frame, and you apply this mask, this non-blindly extracted mask to a mixture, then you hear one source, more or less, with some distortion. So the assumption is quite good, but limited. I cannot assume this for 20 speakers, but I can assume this for 5 speakers for sure. Yilmaz and Reichardt already mentioned 10 speakers together. I could not reproduce this, but 5 I could reproduce quite easily. So this assumption is quite valid. So then, for each time frequency beam, I actually assume that there is only one source eta L, and it has a probability of being active. And if I take out all the noise-only frames, then the probability of all speakers to speak in the current frame will sum up to 1. This will be important for us later. Now, we mentioned the latent RTF before, but now I calculate something which I call the instantaneous RTF. So just the ratio between two microphone signals at a specific time and frequency. This also is a reminiscent of the RTF, but it's not the real RTF, but rather called the instantaneous RTF. So if we look at these instantaneous RTF, then we really depend on the activity of the speakers. So let's assume that we have 3 speakers, a red one, blue one, and a green one. This is the RTF vector, all the concatenation. Here I wrote 10 boxes, but it can be, it's usually a few hundreds. So the number of microphones times the number of frequencies. But let's assume that we have these 3 speakers. And then if you look at the first frame, you can see that it's rather mixed. So all the speakers are active, but each box here is, of course, dominated only by one, as you see here. But however, if you look at the second one, you can see that it's mainly blue. And on the fourth one, it's mainly red. And on the green one, on the fifth one, it's mainly green. So this means that if I would be able to extract, to look at frames number 2, number 4, number 5, I have a very good access to the activity and the RTFs behind it of specific speakers, the blue and red and the green speaker. So this will be very important for us in order to decide which frame is good for us for the estimation and which is not. So now I take an expectation. Usually I don't take expectation, of course, since I don't have the probability density function. Usually we take the one, since the vectors are very large, we can take one sample out of this expectation and will be good enough, and what is called typical series. And we can show, I don't want to show it here, the proof is at the appendix if you're interested. And so it's clickable, you can go there. So you can see that this correlation becomes something which is related to the multiplication of the probabilities. And if we use this in a matrix form, we can construct a correlation matrix which its L and N entry is actually only constructed from P. And it can be written as P times P transpose. What is important here is the fact that P is a matrix of L, which is the number of frames that I process, usually long, very long, very large number. I don't know, tens of frames. And J is the number of speakers in the scene, which can be 6 or something small. So this matrix is really rank deficient. Its rank is J, and it's a large matrix. You can see it here, but it's rank deficient. This will be also important for us. Since this is rank deficient, I can apply eigenvalue decomposition, and then I can see what is the number of speakers in the scene. So for instance, here, we can see that there are only 3 major eigenvalues. All the eigenvalues which doesn't exceed a predefined threshold or some threshold that we extract from the data, all of these eigenvectors are discarded, and we use only the dominant eigenvectors. In this figure, there are only 3 major eigenvectors, which you can see here. And since the matrix was rank deficient, we see that this matrix of eigenvectors is actually related by a linear transformation to the matrix P. So the matrix U is related to the matrix P. And then if we look at a specific frame, we here see that there are 3 eigenvectors. Then we can see that if it's a vector that of mixed signal, it will go to one of these yellow points. If it is dominated by one speaker, it will go to the edges. I will talk about it in the next slide, but these edges are the vertices of the simplex that we see here. So let's talk about why do we have this simplex. So it's all related to the fact that all probabilities should sum up to 1, as we discussed before. So each point, L, the probability of this P1 until Pj, is actually a summation. Maybe it's easier to see here. So for instance, for 3 sources, P1, P2, and P3 can be written by this combination. The vertices will be dominated by only one of the speakers, and then it is a point or a cloud of points which are dominated by one single speaker, which is important for us for the extraction of the activity pattern. And since they sum up to 1, they form a simplex. Here, for instance, this is 3 sources, here colored according to the first speaker, to the second speaker, and the third speaker. If we have only 2 speakers, it will be a line, 3 speakers, triangle, and hopefully here, this is a tetrahedron. So these are 4 speakers concurrently. Okay, so now I want to extract these frames that we understood that are very important, these frames, these vertices. And there are algorithms to do this. We use this specific algorithm. I think there are many other algorithms to extract vertices or simplex. And then we take actually a cloud around this simplex. And then we transform it from the U, which is the eigenvectors, to the matrix P, since they are easily transformed between each other by this matrix Q, which we can extract. This leads us to our task, to the diarisation task, first of all. And in the diarisation task, we just look at these probabilities per source J. And if it exceeds the threshold, we decide that there is this speaker is active. So this is why Ij of L is active if its probability of activity is high enough. And if it's below the threshold, it can be set to 0. So this is one thing. Another thing is Lj, which is just collecting all frames in which one of the probabilities exceeds a certain threshold. And if it exceeds a certain threshold, these Lj will be used will be used to extract the RTFs and everything that we need. This LJ that we discussed before. Of course, this we can also enhance by the video, I think. Here we want to be a bit more conservative in the fact that we have a higher threshold or some type of hysteresis in order to take in only frames which we are really sure that are dominated by one speaker. So you see that like the green ones, the red ones, the green ones are depicted here, the red ones are also here, and the blue ones. The red one is less active, but we can still extract it. We have some method to extract also less active sources. By the way, for less active sources, we might think that in our scenario, the patient will be less talkative than the other parties, like the doctor or the robot or the family that comes with the patient. But we still, when the patient is speaking, is very important, and we also have method to extract sparsely active sources as well. I did not want to talk about it here.
Sharon?
Yes.
In this, you are assuming that the speakers are static, right? They don't move.
Yes.
Because over time, it's the same eigenvector, so it's the same.
Exactly. I would emphasize this also in the end of the talk, but I can already say now that if you limit LJ to a fewer number of frames and then use it also in parts, so you split the signal into parts, maybe take only for each, when you want to estimate a specific activity, you only take past frames, but then you take only a few frames, then you can update it once in a while. The only thing that you have to take into account is how to associate the eigenvectors that you estimated, or the simplex that you estimated in one, let's say, batch of frames to another one.
Yes.
We actually did this. We were analyzing. First of all, you will hear soon something that we did recorded in our lab, but we also analyzed the sessions between in psychology sessions between the patient and the psychologist, and then the psychologist is not speaking too much, but the patient is speaking his heart and is speaking for very long periods. So the activity was very unbalanced. This is one thing. And another thing is the fact that the sessions could be 1 hour sessions, so we cannot process it on our computer. So we had to split it into small segments, I would call it. And then we found some way in order to associate them between these segments. Of course, if they are really moving, the association will become much more difficult. Another thing that I can say, which we didn't try here, but I tried it in other algorithms, is the fact that we know how to apply eigenvalue decomposition and also major eigenvector extraction recursively. There are methods from back from the 90s, which are called PAST or PAST-D, which are estimating the dominant eigenvectors dynamically, LMS type of algorithms. I was thinking that we can apply this in this project as well, but we didn't do it yet. Okay. For now, I would say that the solution will be to split the signal into segments, short enough segments, and then associate between them, which we already did.
Okay, thanks.
When I present the results, it's real speaking people. They were sitting around the table, so they didn't move too much, but still they were free to naturally move in their seat. So some movement is allowed by this model without any problem. If you really want the robot to walk with the patient, then you need to do something more sophisticated, which we haven't done yet in this context, but we've done it in other contexts. Okay, so let's go to some validation. We start with more static validation, for which we use the database of acoustic impulse responses that we measured in our lab. There are 6 speakers here, 6 speakers, 4 microphones only. You can see it here. And but we assume that only 2 speakers are concurrently active, and we took 24 seconds. and where there are some parameters which are not important. And this is an analysis of one of the segments. Later I will play some sound files. So this is an analysis. So we have the reversion time 360 milliseconds, like an office. You also have this database 610, which is like it's larger than the waiting room that I measured in the hospital. And here you can see the real activities without the hat and the estimated activities. You can see that it's quite good, but we have also numbers. These are the probabilities. The probabilities are soft. They become hard after you apply some thresholding to make P, to translate it to I. But here you can see the probabilities. You can see also that the activities are quite nice. So these are the activities of the 6 speakers. These are some average results. On this scenario, this is completely static scenario since it's simulated. I will go later to real recording. So we always identified in each of the trials, 20 trials, we identified that there are 6 speakers in the scene. The diarisation accuracy for these 3 reverberation level was very high, around 99% for the 3 reverberation level. So the activity of each of the speakers. And of course, since this is a noiseless problem, we can have an SIR, which is the speech to interference separation, only in the frames in which they were concurrently speaking. You can see that we started by equal level of the sources and we reached 25 dB, which is very good, but this is due to the fact that it's very static and noiseless. And the SDR is also there, so the distortion is relatively fine as well. Before going to a real example in which we have noise, I would like to discuss what are the changes that we have made in order to deal with the noise. So first of all, if there is noise, I cannot just assume that there is only one speaker active, one acoustic signal active, since the noise is always active. So these are the sets of noise-dominated sources. So for which, for this, we define S of J that we had before. It's the set of all active sources. So this one is the activity of source J is the L and K bins in which there is one source which is dominant than all the other. And N is the complementary set in which only the noise is active and all the others are inactive. What is happening if there is noise? So I go back to the same figure that I had, more or less the same figure that I had before with the 3 speakers, the red, the blue, and the green speaker. But now some of the bins, TF bins, will be dominated by noise, which you can see here. So these are there with these diagonal lines, and this should be not part of the estimation. So now we want to apply, since we cannot only work in frames, since the noise is everywhere, and some of the frames will have a lot of noise. We want to introduce another simplex-based complex. So one of them is that we do the same thing as we did before with a simplex analysis, and this we do globally per frame. Now the summation will not be 1, but smaller or equal 1 due to the fact that there are some noise samples. The simplex will become larger by 1 all the time, since there is another vertex for the noise, the J plus 1 vertex, which is always in the origin of the system. This is for 2 speakers. But there is another set or another vertex which is related to the noise. But we want also to work locally per frequency. Why do we want to do this? What are the problems? So we want to do this due to the fact that some frequency bins are good for us and some are not. So we want to estimate some type of a mask. This is one thing. Another thing we must take into account is the fact that if we apply this simplex analysis per frequency, then we need to organize them all together according to the same global simplex. If we do not tie them together, then for each, the separation of each frequency bin can be permuted. So we have to tie them together to the same global decision. So this we do here by taking this weight vector, which is related to the local distances that I apply here, and they are all weighted by or tied together by the global simplex analysis that we mentioned before. So we have global probabilities and we have the local mapping per frequency. And based on this, we select the most dominant source and apply a mask for this dominant source. We know that we can do this due to the fact that Ilmaz and Reichardt in their work on WDisjoint orthogonality are telling us that each time frequency bin is dominated by one source. So we can find the dominant source. I call it not exactly the mask, it's related to the mask, it's the dominant source per time frame L and frequency index K. So it can take the values between 1 and j plus 1 when j plus 1 is noise only frames. So now, what do? We want to apply the LCMV beamformer that we mentioned before. So we do this. We define a mask based on this M that I just defined. It becomes IJ becomes 1 if MLK of equals J. So if it's dominated by the J source. I take only the frames which are dominated by the noise, the J plus 1 class, and estimate the noise. This may be related to your question before, Chabi. This we can use also for, we can use it recursively. So rather than taking the entire set of frames, we can apply this recursively by some type of RLS estimation, and only use frames which are dominated by the noise, or maybe do it a bit more soft. We did it once, a bit more soft with the probabilities. So this is for PV that is needed here. For when we extracted the frames which are related to the J source, we can estimate the correlation matrix of this source. It will be a noisy correlation matrix. This is why we apply generalized eigenvalue decomposition, and we take the major eigenvector. Since we know that these frames are dominated by only one source, we take this in order to apply the beamformer. So we apply 1 towards the desired source and 0 towards all the others. If there are multiple sources which are of interest, as we have in the project, then we can apply multiple beamformers, and we'll have, for instance, 3 outputs, and all outputs will be on different streams, which can go to the cloud as well. So in general, we have the LCMV beamformer as the heart of the algorithm. It also have, on top of it, at the output, we have this spectral mask, which is related to this I. We can use it as a mask. It is depicted here. And we have a control algorithm. Radu asked about control, which we call it the GLOSS algorithm, global and local something, source separation. I forgot what is the O. So let's also talk about the real experiment that we did in our lab, unless there are questions. Okay, we can have, we still have 2 or 3 minutes to finalize, and we'll have time for questions. So we have people who were sitting around the table. There were noise sources around. There were microphones in the perimeter of the scene, and also on the table. We can use whatever. So the database, we didn't make it public yet, but of course we will do this. But it will be already available for the project. So there are multiple native English speaking people that were speaking in the lab and sitting in these 6 chairs. We recorded them separately, but we can mix them whatever we want, and together with this we have noise, and we have 32 microphones for which they were recorded. So some of them are in the form factor of cellular phones, some of them are around the table, one of them is a long array, so we can do many, we have many options here. So this is a bit black, but this is a picture of the lab with the time. We flip the panels to change the reverberation level, and you can see here the microphone and some microphones around, and these are the tables. And numbers are nice, but maybe it's good to listen first. So first I will play the mixture. It's one of the mixtures.
I'm sitting on chair 5 in front of
chair 6.
My name is A. I'm sitting on chair 3 in front of mock-up. The researchers recommend strictly limiting consumption of added sugar. The letter, which was first reported by Green, follows employee-driven campaigns at Microsoft
Consumer intelligence researchers.
So they are not concurrently speaking, but they have a very large overlap between them. And I would like to extract each one of them separately. So for instance, the first speaker.
My name is A. I am sitting on chair 3 in front of mock-up C. The letter, which was first reported by Green, follows employee-driven campaigns at Microsoft and Google.
First one, maybe another one.
My name is H. I am sitting on chair in front of mock-up F. The North American beverage business, which accounts for 1/3 of total sales, has been pushed by increased competition.
And so on. I have more, I can provide more examples, and I also have more examples in my website. So I think quite clearly they are separated. There are some artifacts. It's very noisy. Most of the time there are 4 speakers speaking at the same level and more or less concurrently. Usually, or hopefully, we will not encounter this problem all the time, but we can cope with it. There is some type of, I would say, a bit of instability, but not too severe, and some musical noise, which I think we can improve by having this eye indicator a bit more soft. With this, I think we can play, but this is the raw algorithm as is. So this more or less concludes what I wanted to say today. Maybe just as a summary, I started the talk today by saying that we want to use the acoustic propagation. It really helps us. So we can also even separate sources. We also did some experiments with this to separate sources which are the same line of sight. This is something that is very unique to the algorithm that uses the acoustic propagation and not only the angle of arrival. And we use the RTF, as I already explained. There are some extensions which are less important now. Dynamic scenarios we already discussed. This is still a challenge. We have some method. This is the paper that I mentioned about this PAS-D, which is this paper that utilizes PAS-D in order to estimate the eigenvalue decomposition recursively in an LMS type of algorithm, or LMS or RLS. It depends. It depends on specific implementation. Of course, this becomes more challenging, especially if the microphone array is moving. We already started with other algorithms to check what is happening if the microphone array is moving. But this is will be a topic for another discussion. We still have to do some work here. It's not done yet, but I think it's already encouraging the fact that we have a very, let's say, harsh condition in which 4 speakers with noise are speaking, and we are able to extract each one of them quite naturally. And there are real people that are free to move on their chair, but they are not loudspeakers or something very stable. So it's just real people. And this is just a big thank you to many of my former students. There are more collaborators, but just So some of them are still working in the project. So I think this will conclude what I wanted to say today, and we can leave something for other talks as well.